All right, welcome to Unit 2. So, Unit 2 is titled Equilibrium. That's going to be the main theme of this entire unit. And it's going to be broken up into 3 lessons that we're going to do over 4 days. So, it's almost like there's 4 lessons, but the third lesson is just so big that we take 2 lessons to do it. The first lesson that we're going to do today is broken up into equilibrium, spontaneity, and Le Chatelier's principle. And we're going to start with the concept of equilibrium, specifically what we call dynamic equilibrium. So, dynamic equilibrium occurs only when you have a closed system. So, a closed system is something where there can be nothing that enters or leaves your system. If you have a closed system, most chemical reactions are reversible, meaning that the forward and the reverse reactions are possible, and in fact, they occur at the same time. We represent this by using a double arrow. Now, you'll notice throughout this lesson, I use different variations of the double arrow. It kind of just depends on what editing software I was using. So, this one's kind of like a nice forwards arrow on top of a reverse arrow. I often simplify it just to an arrow or a line that has arrowheads on both sides. It doesn't really matter how you draw it. The key thing is that your forward reaction and your reverse reactions are possible. So, a great example of this is colorless, let's see if I can say this right, dinitrogen tetroxide, right? That can compose into brown nitrogen dioxide. But nitrogen dioxide can also recombine to form dinitrogen tetroxide, depending upon the conditions. So, a visual of this is starting with that colorless dinitrogen tetroxide in a bottle. So this is a closed system because it has a lid on top. Nothing is entering, nothing is leaving. When you start this reaction, initially it is pretty much all dinitrogen tetroxide. So the concentration of the dinitrogen tetroxide would be high, and the concentration of nitrogen dioxide would be very low, like maybe even 0, right? There might not be any. So if you could, no substance is ever pure, but if you're introducing the N2O4 and it is purely colorless, then probably at the beginning it's not going to contain any NO2, but it's really hard to make reactions not happen. So I'm going to say low to 0. When we start this, let's say that this test or this whatever jar is colorless. Now it's got a little bit of a tinge of brown because there is some of that nitrogen dioxide present, but let's just say initially this is where we're at. The forward reaction would be very high. You have lots of reactants present and very little products. So for the reversed reaction to happen, you're not going to have 2 nitrogen dioxide molecules to even hit yet. So we're going to say that the reverse reaction is 0. Now I've got this shown in the picture above, just visually, but there's also these charts at the bottom of the page. So where we're at right now is the beginning of the reaction. The concentration of the reactants is high. The concentration of the product is low. The reactant being the N2O4, and the product, sorry, my 4 is always turned funky, and the product being the NO2. Right? So initially you have a high concentration of N2O4 and a very low concentration of NO2. Initially, your rate of your forward reaction is quite high. So if you think back to Unit 1, if we did an instantaneous rate at the beginning, the slope would be quite steep, right? It's decreasing, but this rate, even actually without talking about slope, if we were to take a point in time, the reaction rate here is quite high, and the reaction rate here is quite low, in essentially 0. Then what we're going to do is we're going to approach equilibrium. So we're going to say we're maybe somewhere along the lines of here in our diagram. As you're approaching equilibrium, the concentration of the dinitrogen tetroxide is decreasing, whereas the concentration of nitrogen dioxide is increasing. The color is going to be maybe like a light reddish brown or a light brown. As we produce more of the NO2, the reaction is going to get browner and browner. The forward reaction is decreasing. You are using up some of those reactants. So the rate of the forward reaction, it's a negative slope, meaning the rate is decreasing, whereas the rate of the reverse reaction is increasing. Now, if we were looking at this on the graph, you'd see that the concentration of the reactants, there's a steep decline at the beginning, and then that steepness kind of levels out, right? So we have initially a very high concentration of reactants, and it drops quite quickly, and then that dropping kind of slows. So that decreasing in concentration is slowing over time. And same thing with your products. You have this steep increase in products, and then all of a sudden that kind of slows. So as you approach equilibrium, you know, your concentrations are decreasing or increasing, and that starts out fast, and then it goes to slow, right? Same thing with my forward reaction. You know, originally it's high, and then it's decreasing, but then that rate at which it's decreasing is slowing over time. And same thing with the reverse reaction rate. It is increasing, and then the rate at which it's increasing is slowing over time till we reach equilibrium. At equilibrium, what's going to happen is that your concentration of the dinitrogen tetroxide is all of a sudden going to become constant. It's going to stop changing. The concentration of nitrogen dioxide will also be constant. The color will be a constant brown. And it's a bit darker now, so let's say a constant darker brown. And then the forward reaction rate is constant, and the reverse reaction rate is constant. Everything levels out. The other thing I want to point out is that the concentrations are constant, but not equal, whereas the reaction rates are constant and equal to each other. So if you look at this chart here for the concentrations, the concentration of this is NO2. So the concentration of nitrogen dioxide is constant, and then the concentration of dinitrogen tetroxide is constant, and they're not equal to each other. And if you look at this one, you actually have way more nitrogen dioxide when the reaction hits equilibrium. And then the reaction rates, they kind of came into each other. The rate of the forward reaction decreased, the rate of the reverse reaction increased until they reached a constant rate at which they're at equilibrium. Now, this is called dynamic equilibrium because your concentration of your reactants and your products is going to stay constant. It's not going to change. You are making dinitrogen tetroxide from the reverse reaction. You are making nitrogen dioxide from the forward reaction, but the concentrations aren't changing. So as soon as you lose dinitrogen tetroxide, the reverse reaction is making more, right? And the same thing, as soon as you use up that nitrogen dioxide to make the dinitrogen tetroxide, then the reaction goes forward and makes more. So it's called dynamic equilibrium because even though you're not seeing any big changes, your concentration of your reactants and your products is stable, but the forward and the reverse reactions are still happening. So if you look at the color, right, the color remains constant because you've got that forward reaction happening, but it's not going to get any darker because that nitrogen dioxide is getting consumed at the same rate as it's being produced. So to summarize dynamic equilibrium, this is a really important sort of summary here. The forward and the reverse reactions, when you reach dynamic equilibrium, they are going to be equal and constant. Actually, let's put that in the reverse order. Let's say constant and equal, just because it'll work better with the next fill in the blank. Oops, I didn't change it. Constant. I really want to write it that way, don't I? Constant and equal. The concentrations of the reactants and products are also constant, but the concentrations are not equal. See why I wanted to put it in that order? The equilibrium is called a dynamic equilibrium because reactions continue at the microscopic level. There is a making and a consuming. I was like, what is the opposite of making, right? You are producing and consuming nitrogen dioxide at the same rate as you are making and consuming dinitrogen tetroxide. So you don't see any macroscopic changes, but you still have reactions continuing at the microscopic level. So equilibrium is called dynamic because reactions continue at the microscopic level, but there are no macroscopic changes. The easiest way for me to think of this is that the reactions are still happening at the microscopic level, but the concentrations are not changing. Now, very key, equilibrium can only occur in a closed system. If you allow things to escape or enter, then you're changing things, right? If you have reactants turning to products and those products are gases and they escape the container, how are they going to reform reactants, right? They can't, they're gone. The other key point is that equilibrium can be approached from the left. So you can start with reactants or you can start with products, right? You can have your start with your products, goes to reactants, and then all of a sudden you'll reach equilibrium. All right, go and try those practice questions.